Hello everyone, my name is Komal Marathe. Today I am presenting my final project for DA5030. Title of my project is Predicting Cancer Treatment Status from Cancer Data. I chose this data mainly because I have clinical experience and I'm currently in bioinformatics graduate program, and I've always been passionate about the advancements in cancer treatments. So the main goal of this project is to build various machine learning models to predict if the patient is will be treated or not treated based on the treatments that he or she has received. So dataset that I used in this project was obtained from cBioportal for cancer genomics, which is maintained by Memorial Sloan Kettering Cancer Center. So this data contains approximately 24,000 patient observations with 51 features across the data. These features mostly contain the treatment information, which is basically if the treatment whether the treatment was received by the patient or not. And the target variable for this data is the treatment status, which is treated and untreated. For this project, I have chosen three algorithms to work on, which is binomial, which are binomial logistic regression, random forest, and naive Bayes. And to perform on this project, I have used CRISP-TM method, which is where I followed business understanding, data understanding, data preparation, model construction, model evaluation, and model tuning and performance improvement. So here is the code for the project. So I loaded the data using the Google Drive link because I've hosted the data publicly on Google Drive. For the data exploration purpose, I checked the structure and summary of the data. As you can see, most of the variables are character variables. They are basically the various treatments that patients received, and the value is basically yes and no, if whether telling us whether the patient received that particular treatment or not. For I did create a lot of exploratory graphs where I first plotted the continuous variables that are present in the data, which are basically the 5 variables, and I've also plotted categorical variables to understand the frequency of various values. For example, here I have plotted cancer type that is present in patients, and try to see the frequency of some cancer types in various in men and women. And here I tried to see the frequency of cancer in various races, and also here I tried to see the treatment status for every cancer type. So as you can see that there are 3 types of treatment status: untreated, unknown, treated. As I wanted to predict the treatment status for if it was treated or not, so I removed the observations with the treatment status unknown. So for the outlier detection part, I checked the summary of every continuous variable and tried to look at the minimum, maximum, and median and mean of these variables. Most of the outliers that I got were not really abnormal for me because, for example, the age of the patient. Now, here it says that the age is almost zero, which is basically fine because there are some newborns that are born with cancer. So things like that didn't really feel like outliers, and I didn't want to lose any important information, so I didn't eliminate the outliers here. I also created correlation for uh, for continuous variables, as the treatment status was also categorical. I only tried to identify the correlation between continuous variables, and I did check the correlation of all the variables with treatment status later when I convert the data into the categorical data into factors. I also eliminated various columns with redundant information, such as study type, a study ID, sample ID, uh, cancer type in detail, oncotree, which were basically the same information, and or or it was not really useful. Um, but I made sure that while eliminating these columns are actually irrelevant. For example, the study ID and patient ID, these things would, if they are in integer format, then they can affect the machine learning model. But here they were not. But I made sure that each observation is unique. So that is what I did over here. And after checking that, I removed all these irrelevant variables. I also did data imputation where I imputed the missing values for both categorical and continuous variables. For the categorical variables, I imputed missing values with the mode of that particular column. For that, I created a function. And for the continuous variables, I used median to impute the missing values. I didn't do any dummy coding because my algorithms were the algorithms I chose were able to work with the factor data, so I converted my data to factor instead of dummy coding the variables. Yeah, and after that I checked the correlation of treatment status with various all the variables. I couldn't plot the uh, all the 46 variables together over here. It gave me some error, so I divided them into 5 parts where I kept the treatment status in all 5 and checked the correlation of treatment status with all other variables. For the transformation of features part, I so many I only had 5 continuous variables. So I tried to plot their distribution again over here using histograms, and I tried to use various transformations like log transformation, square root transformation, and inverse transformation on each continuous variable, but none of them actually worked, so I kept the data as is. But I did standardize my data, my continuous variables, using z-score standardization. uh, I used a scale function for that, and I considered using z-score standardization as I wanted to keep relevant outliers in the data, and z-score standardization works well takes care of that. So I didn't. So I used the Z-score standardization. I also did principal component analysis for the data, which was yeah. Now let's go to the model construction part. For the model construction, I uh, firstly divided the data into two parts. I use 75 to 25 proportion, and I use create data partition for it for so that uh, there basically it followed the stratified sampling to maintain the almost equal proportion of class variables into both the uh, training and testing data. So first model I you created was binomial regression. Here I tried to create the model using treatment status with all the features. Interestingly, I after creating the summary of the model, I got a p-value as 1 for each variable, indicating that none of these are significant. I tried to use a uh, step function to create the backward elimination of insignificant variables, but it left me with two variables after that. I tried to run this again, but it it was really long, and uh, output was also like really verbose, so I didn't include it in the file. So I kept the first model only for the as the final model because this also didn't actually give me any. The step function also didn't give me any significant uh, variables, so I kept the model as is, and I tested it on the test data and created its confusion matrix, where I got the accuracy of 1, which is basically 100%, and kappa also 1, so which was really surprising. Second model I chose was random forest model. Here I use random forest function from the car package and uh, created the data using all created the model using all the variables. So while creating the model, it was able to classify correctly all the patients into correct categories with uh, almost no error. And I tested the data with uh, the validation data set that I created previously, and it also showed me the accuracy of 100%. It correctly categorized both the types of patient into correct categories. The third model I used was naive Bayes. Uh, I use this model mainly because it works well with the categorical variables, and most of the variables in my data are categorical. I also tested this model on my validation data set, and it also gave me a really good accuracy, which was 93%. For the model evaluation part, I used the holdout method, which is basically creating two different data sets to train the model and test the model. and accuracies were really good for this hold out method. I also use evaluation with k-fold cross validation. So I kept the value of k 10, and for each model I evaluated each model using this method and collected accuracies of each model for every algorithm, and created mean of it to check the average accuracy of each model. So it basically creates 10 different models and tests all those 10 models and collects the accuracy. So from this method I got really good accuracies again, which was basically 100% for random forest and logistic regression and 93% for naive Bayes. I also tune the hyperparameters of each model, and I use train function from carrot package to do that, and predicted values for treatment status for the whole data set with using the train method. Sorry, not train method, the tuning hyperparameters. And for that I created confusion matrix to see whether they classified uh, each patient into appropriate treatment status group. So yeah, for here somehow naive Bayes didn't work well. Naive Bayes classified untreated treated patients, all treated patients as untreated for some reason, which was weird because it performed well previously. So I also constructed an ensemble function the for the random using the random forest, because random forest was the one that performed the best among all three for all the even after tuning the parameters and for the holdout method and k-fold cross validation. So now to wrap up my presentation, I think all the algorithms that I use performed really well. Random forest was the best one and to perform, and also um, there were certain learnings that I gained from this project. That the data exploration and preparation took really long time. I think most of the time was spent on that part, and I also realized that even um, though the models perform well, I was not sure why. So knowing pros and cons of algorithms and pros and cons and knowing every model in detail is really important if it to basically evaluate and understand what is going wrong, if something's going wrong. So yeah, thank you so much.